Hi, this is Dr. Liu. In this video, I will explain what are forces and Newton's laws with simulations. So forces are simple concepts to start with. You all know what forces are. They're push and pulls, right? So those are easy to understand. But what is not that easy to understand is you need to consider all forces from all sources that could exert forces, not just from your human point of view of you yourself exerting forces and ignoring some other sources such as the earth could exert gravity on you, and surfaces could have friction against your vehicles, and so on and so forth. So with our intuition, sometimes we can get things right and other times we get things wrong. So let's try to explore maybe both directions so you know how much you should rely on your intuitions with forces. So with this, let's take a look at the first law of Newton's laws of motion. The first law says objects at rest stay at rest and objects in motion stay in motion. And this is pretty easy to understand. The first part, objects stay at rest, stay at rest, right? You have an object that's sitting on your table. It's been sitting there for a while, and it just continues to sit there, right? But the other part is harder to understand. Why that object in motion will stay in motion, because that part is against our intuition. For example, you push something. It could be your say your couch in your living room. You have this big couch, a three-seater. It's pretty heavy. You want to move it, and you exerted all the force you could. You started to push it, and you push it into a position, and then you let go, and the couch just stopped immediately. I want to put quotes around immediately. But that's what you experience, so that's what you're going to use as intuition to understand physics. And I'd like to show that with a simulation. So let's bring up the simulation. So this simulation is from a PhET from University of Colorado. So what we see here is there's a bunch of things we can do. Here's a little wooden figure. So this is our laborer. This wooden figure is going to push. We can put anything against this figure to have it push. So what I have is we have two 50-kilogram crates stacked against each other. So that's a pretty heavy 100-kilogram mass. And let's see what kind of intuition we have. This is something we should consider. This is just per our intuition. Let's push. Okay, just like you would do these figures, pushing harder and harder. It's just not moving. Think about your couch. Very hard to get it to start moving. Okay, so let's keep pushing, keep pushing, keep pushing, keep pushing, keep pushing, keep pushing. I like this simulation. This wooden figure start to crouch down, try to push harder. Oh, now that moves, and then you let go. It just immediately, I want to say that, quote unquote, immediately stop. So that is all you experience. This figure is you. And you push, and sometimes things don't move. They if you don't push, they definitely don't move. At least these two crates don't. So you push, you push, you push until you start to move something finally. But then as you let go, it stopped. But you probably noticed it didn't stop immediately. Although your couch probably stopped immediately after you let go, you stop pushing. So what's actually what you're experiencing is you as a person or this wooden figure, you are exerting a force. I can't really click and point at the same time, so let me just stop exerting force and point here first. This is the amount of force in Newton. We'll talk about what that is. And this is just a sliding bar that you can I can exert forces just like that instead of pulling on the figure. So you're exerting forces and things don't move because there's too much friction. Think about your couch, right? So as they start moving, so if I just exert that force for a little while and things start to move faster, so that's if I let go and they can slide forward a little bit, although you don't really see that with your couch. It just means you're not really pushing it hard enough for long enough time to accelerate it into a higher velocity so that it would slow down and stop. Just like any accelerated motion that has a negative acceleration, it eventually slows down and stops. It doesn't stop immediately. So that's what we experience every day. That's what we kind of base our knowledge on. But let me tell you this, because I said this before. You need to consider forces applied by all parties involved, not just you. You, the wooden figure, right? The wooden figure pushes, and then things move, and the wooden figure stop pushing, things kind of stop moving quite quickly, right? So there's actually other sources forces. For example, the surface here between the ground and the crate has a lot of friction, and that is a force. So let's display the forces here. So we see what forces are exerted on the crates, right? The crates are the object of interest. We want to see how it moves, how it accelerates. We already have kinematics, right? So now we're trying to understand the dynamics. See, now the orange arrow pushing forward is that of the orange figure, right? That wooden figure, and the leftward force is frictional force. So that is between the surfaces, and there's actually no frictional force if you don't push, right? So frictional force is not an active force that's always there. It doesn't always have to be there. It's only there when it's needed, and here is needed. So as you apply more force, friction actually increases itself, and it looks like the two forces are equal to each other, right? Okay, so let's move my mouse down here. I can pull this lever instead. So it just increases, increases, increases. Looks like friction is always able to counter the applied force. But I don't think that's the case. Because if I keep pushing, friction will eventually max out, and then we should be able to move the crates, right? So that's what happens here. Two parties are involved, two forces: applied force from you or the wooden figure against the crate, and also a frictional force from the ground against the crate. They're equal and opposite, so they render each other's effect null. That's why it's not moving, the crates. So now it's moving. Oh, okay, so now it's moving. Frictional force kind of just suddenly becomes slightly less, so you can accelerate. Oh, now it's only frictional force, so it causes a negative acceleration on the crates. That's what brought the crates down to slow down to stop. It's not because you stop pushing, is because there is a friction that causes that motion to change, right? So if there were no friction, I imagine there would be no reason for the crates to stop, right? So let's think about this one more time. You're pushing, you apply force, but that is not the only force. There's other forces involved, such as friction this time, right? So in order to consider how an object is going to respond to your force, you have to consider all forces acted on that object, including yours, not just yours, right? You're a person, or maybe this is a wooden figure, but that's not the only cause of motion, right? So there are other forces. All forces have to be considered, so you have a complete picture. So when the forces are balancing each other like this, and there's no acceleration, things don't accelerate. So if they don't accelerate and they don't move, and don't move means they have zero velocity. Don't accelerate means they do not change their velocity. If they start with zero, they do not change, then they end up with zero velocity. So that's the first half of Newton's first law. When objects at rest stay at rest because they have no acceleration to change their velocity from a zero to a non-zero. And let's try the object in motion stays in motion, but this is not going to work out too easily because there's friction involved, right? So as you let go, see the frictional force causes the object to stop. So let's move this lever. This is friction lever. So let's move it to none. Okay, we have a very slippery ice-covered surface. So now what's going to happen? Well, what's going to happen is the figure will accelerate the boxes, and then I'll let go of the figure from pushing, so the box will stop getting pushed. But it's already in motion, so according to Newton's first law, objects in motion will stay in motion. That is only because there won't be any force acting along the direction of motion anymore, because friction has been eliminated. So in this case, your force, or the figure's force, is the only force. See that? Just apply a little bit, and you don't have to push harder. See, it's already moving. It's already moving, And let's display a speedometer. Let's keep pushing. Yeah, we just caught up with that with the crits. See, the speed starts to increase constantly. If I apply constant force, if I let go, it just starts sliding away. Okay, so I can try to slow down just like friction would do, right? By pushing backwards, so it'll slow down. But I guess I didn't slow down entirely. So as long as I have no friction, that means no force along this horizontal direction that could affect the motion, the crits will just keep moving. So this is the second part. We don't get to see or experience every day. Well, we're in Minnesota, so we sometimes do experience expectedly or unexpectedly if we're trying to move on ice, right? So this happens. Let's try to slow down. Let's try to slow down. Slow down. Can I slow this down and stop? It'll be really difficult. Think about it. Trying to slow down stuff on ice. Yeah, you have to train yourself in order to use the ice skates to slow down, stop yourself, right? Anyway, so what I meant here is object in motion stays in motion doesn't really always occur in real life, and you'll have some trouble understanding why it happens. So we started with a lot of friction. I think it's just one notch from the maximum, and we try to push, and we do make object move, and when we let go, object stops. That's because there is still a force, friction. It acts against the velocity, against the motion to stop it, right? So once we remove any friction, we can just push and whoa, so just let it go. It'll just keep moving at a constant velocity now, right? So that is an explanation of Newton's first law. So we only get to see this, well, if we're on icy surface, or maybe we're using air tracks where the objects can be air lifted so that there's very little friction, or we're say in outer space. And this doesn't simulate outer space, but if you think about outer space, nothing really stops us. There's no friction between you and the vast vacuum, right? So you could be floating away if you're not paying attention. So that's Newton's first law. Let's stop this, and we can go back to this, and we'll start Newton's second law. Okay, so as we already saw that if we accelerate with the force, and the object starts accelerating, so there must be some relationship between how hard you're pushing and how much your object accelerates, or at least I should say how hard you're pushing against all the other forces pushing, right? So because it's not just you, a person or human being, everything else may exert force, right? So the second law is usually expressed like this: F equals ma. Or no, let's use capital F equals ma. So what this means is acceleration is proportional to force. And the proportionality factor is mass. We know what mass is, right? So let's explore this with a simulation. We already have some ideas. So let's bring this one back, and we'll check a box to display acceleration, and we'll also display the numerical value of it. So the force is already being displayed, and for simplicity, let's remove friction. So the only force that we're going to see exerted on the box is going to be the figure's force, and I'm going to use this to basically exert a constant force. Let's see how the acceleration works. So let's see, let's display masses. So 50 kilograms. Okay, so let's exert okay, so just trying to get exact. So I exerted 50 newtons against 50 kilograms, and I end up getting a 1 meter per second squared acceleration. So I gotta watch my speed, because I think this this wooden figure won't be able to keep up as the speedometer hits the maximum. Anyway, the velocity keeps increasing at constant rate. Let's pause it so I have enough time to talk. So velocity was increasing at constant rate. The acceleration stays at constant magnitude. That's because we have a constant net force on the crate. I can display sum of forces, but that's the same as the applied force because I dialed down friction, right? So let's keep playing it. And what I want you to see is what's going to happen. Okay, let's see what's going to happen. Velocity keeps increasing. I think at some point our wooden figure will be unable to push anymore. Can't really keep up. Whoopsies. There. So now the force is gone. And see that some force is gone. The acceleration is gone. So now we're in Newton's first law. The object in motion will stay in motion at same exact speed. I think that's the best way. The best the wooden figure can help us is to push until that speed, 40 meters per second. That's already pretty fast. I don't know how fast a cheater can run, especially while pushing a 50 kilogram crate. All right, so let's pause and stop it, and so we can rewind. Okay, let's get back to the formulas. So what we just observed was we applied a force, and that was the total force because we turned down friction to 0. So the force was proportional to acceleration. We applied 50 newtons of force, and we had 50 kilograms of mass. So the left side is 50, right? So let's write something down. So we have an example where we have mass equals 50 kilograms, and force applied, this is total because there's no friction, is 50 newtons. And acceleration ends up being 1 meters per second squared. We can calculate this just from that formula because A is equal to F over M if you divide M on both sides. So that is 50 newtons over 50 kilograms, and that is 1, right? 50 over 50 meters per second squared. So this gives us an opportunity to introduce what is a Newton. So a Newton over a kilogram must be equal to meters per second squared. Okay, yeah, if 1 Newton of force applied over 1 kilogram mass, it should cause that 1 kilogram mass to accelerate at 1 meters per second squared. So that's what a Newton is. And if you multiply kilogram on both sides, then you get 1 Newton is equal to 1 kilogram meters per second squared. And sometimes we write that as that's 1 kilogram times meter times second and minus 2 power, either way. So that is how a Newton is defined, is a kilogram meter per second squared. It's a pretty long unit, but let me tell you what this means. A Newton of force will cause 1 kilogram of mass to accelerate at 1 meter per second squared. So that's how much a Newton is. So if you wish to accelerate a 50 kilogram mass to a 1 meter per second squared, you need 50 newtons to do it. So that is the second law. And what I like to do is to next example, I want to expand this into what if we have two forces such as friction and our applied force. Then it should be the net force. So how much forward minus the reverse, and the leftover force, that is accelerating. So let's switch over to the simulation again. And now let's add some frictions. Friction has been reset, which is good, but I just need to get all these displayed. Okay, so let's see. Let's start applying forces. I'm pretty sure friction will try to counter us. Oh, it did. Right, so okay, 50 newtons, applied 50 newtons of force, and friction is matching against me with 50 newtons. So let's add more forces, and friction seems to just match up, but there's gonna be a maximum, right? So let's try to be a little more quickly. Okay, yeah, that'd be too quick. Okay, I think I just I went a bit too quickly, so let's apply 100 newtons. Okay, so So I keep adding more forces, friction will match up. There's a maximum that you can experience friction-wise before your object breaks free. So let's get to that point. Oh, there we go, about 125 newtons. So now friction actually gets less. That's because once you start moving, let's pause it. Once you start moving, it's easier to move. Think about the couch example. You have this big couch, it's heavy, and it has four feet that are dug into the plush carpet. So they make these 4 big holes. And as you start pushing, you have to get the 4 feet basically dislodged from the carpet, and that requires more force than as you actually have moved it out of the holes, and you start sliding it across the carpet, right? So as you slide across the carpet, and it's a little easier. So that's why the friction actually went down. So there will be a difference between the two. And you have 94 newtons of friction and 127 newtons of applied force. So if you subtract the two, 127 minus 100 is 27, and plus a 6 is 33. So that's a sum of forces, or net force, right? The forward minus the reverse. So 33 newtons of force acting on a 50 kilograms mass. So the acceleration should be force over mass. So that over that, 33 over 50, or 66 over 100. So 0.66 is the acceleration, right? So let's switch back to our calculation. So another example. This is example 1. So example 2, we have a mass which is still 50 kilograms. We have this applied force from the figure, so that is, let's call it applied force from figure. Let's call it 1. Okay, so 127 newtons. We also have this friction. I want to put a K here for kinetic, which means you're experiencing this friction. You experience it when you're actually moving. You're in kinetic motion. This is 90. Let's take a peek at 94. Okay, 94 newtons of friction. So F net, which is defined as sum of the forces. So this is sum of forces, which is 120. Let's not do that. Let's get the symbols first. This force minus this force, because we're moving forward against that friction that's backward. So that's 127 minus 94. So let's see. Okay, 33 newtons, right? So I got 33 newtons, and according to Newton's second law, let's rewrite it as net force equals mass acceleration. Now that we have more than one force, then we'll have 33 equals 50 acceleration. 50 is the mass in kilograms. So we have acceleration is 33 over 50, or 66 over 100, so 0.66 meters per second square. So that's what we're experiencing in that simulator. So let's bring that back. So with that acceleration going on, the velocity will keep increasing at 0.66 meters per second every second. So after 1 second, this will be that plus 0.66. After 2 seconds, this plus twice 0.66. So let's have it just run for a little bit. Okay. So it's accelerating slowly. All right. So let's do something else. Let's see. 100 kilograms. That's really heavy. Let's just put a second box on top. Okay, so we're slowing down. See that? Our speedometer is going down. Let's pause and think. Okay, so now we have 2 boxes, and somehow the friction has doubled, 94 to 188, right? So let's not worry about the reason that it doubled, which is a later discussion. Let's just worry about the fact that the friction has changed, right? So now the net force is actually more backwards, right? 61. So the acceleration will still be in accordance with Newton's second law. We just have to recalculate it. So let's get back to the calculation. So now we have F1 is still 127 newtons, still pushing as hard. Friction, on the other hand, is twice that, so 188 newtons. So now our net force is still force applied minus friction. So 127 minus 188. Okay, let's calculate 8 minus 6 and 4 2 is 6, right? 61 negative. Let's put these things apart. So let's put the negative here, 61 newtons. So if force is proportional to acceleration, mass is always positive mass. Then the negative force net means you have negative acceleration. So this is equal to mass acceleration, which is 50 kilograms. Oh, sorry, 100 kilograms, because now we have two boxes times A. So that we can calculate A is equal to minus 61 over 100. So our acceleration will be minus 0.61 meters per second squared. So every second we'll have our velocity subtracted 0.61 meters per second away. Alright, so let's go back to the simulation, see if that's confirmed. So 0.61 meters per second negative. So I'll just let it run for a little while. And you can see the speed is actually getting less and less. So this will run for a little while before it actually stops. I wish I could manipulate the time a little bit, but well, looks like just by talking I did manipulate the time. Whoa, look at that. So as it stopped, the friction actually went down. That is interesting. It was 188, right? Yeah, you saw that. It was 188, but now it went down to 127. So why is that? So I'll leave that to the next introduction of the actual forces, friction and normal force and gravity and such. So I just want to bring to your attention that when something's not moving against your friction, against your force, despite you apply force, that means friction is countering you. So that friction is countering you to the exact point that it makes a zero net force. So let's return to the Newton's laws. So one last law here, I want to just basically type it up, is the third law. But the third law is slightly different. Okay, so the third law talks about forces of action and reaction. Let's just type it up. So forces of action and reaction are equal and opposite. And I also want to add well, just kind of verbally, they're acted on different objects. So our simulator doesn't really show this. Let's go back to the simulator, see what I was looking for. So I was looking for this. See, the wooden figure applies a force to the crate, the orange force. And the crate also applies an equal and opposite force against the wooden figure. Not the friction though, right? The friction is not between the crate and the wooden figure. The friction is between the crate and the ground, right? So what I meant here was if you push, you get pushed back, right? And the action and reaction, they don't necessarily have to be the active person or an animal, something animate that can act an active force. That's not. So the forces of action and reaction, we do not distinguish which one is the action force, which one is reaction. We just call them a pair of action reaction forces. And they're always equal and opposite. Say the figure is pushing the boxes, crates at the 127 Newton force. The crates will push back at exact 127 Newton force against the figure. It will be showing up on the figure, except that this simulation doesn't show how many forces are applied to the figure, right? Only the box. So let's get back here. So what I'll do is I'll just draw something. I'm pretty sure I can redraw the figure as well as that simulator can do. So let's see. Pushing, bending knees. Okay. Stack of 2 boxes, right? So there's a force that the box feels. Basically, it's like this. This is, if I want a very long subscript, I can do it now. Figure on crates. So this force is figure applies a force on the crates. And also the figure, at the arm, I'll just draw from the figure itself. There's this force is crate on figure. Okay, so these two forces are equal and opposite. And they don't act on the same object, right? Otherwise, they will enter into this equation, something like that, and somehow they just cancel each other and there's no motion. It's not that case. So what this case is, the crate feels force from the figure, and the figure feels force from the crate. So if I call these forces by their shortened subscript, so F on crate, that is the same as negative of crate on F, the figure. So that's what the Newton's third law is. So think about this. Say you're being pulled by Earth's gravity downward, right? And at the same time, you're pulling Earth up with the same exact amount of force upwards. So it's not like you're feeling the force. You're the only person or object between you and the Earth. The Earth also feels you because you're pulling it upward. Thank you.